Hey guys, welcome. Today is about nonlinearity once again. I talked recently about this topic with Lukasz Skopny on this channel, and we will be also bringing more topics to you in the future. But for now, I thought it would be a good idea to just maybe point something out to the HyperWorks universe where we could also cover nonlinearity. It's more an introduction to this topic because, yeah, I'm not an expert in nonlinear FE analysis, as Lukasz certainly is. But I know the basics, and I think it would be best to just walk you through an example. This will maybe not be as smooth as you are used to in this channel or on this channel, but I think it's also good if you see me struggle sometimes. Then you can also see how I solve this problem or how I tackle those things, which definitely will come up. So what I did was I prepared here just the tutorial file. So this is a nonlinear implicit analysis of a bending of a plate. So yeah, first off, let's talk about different sources of nonlinearity. We touched on that briefly in the last video, but I wanted to make it to summarize it a bit. Let me go to a tablet here. So nonlinearity means that something is not changing constantly or proportionally linear, right? So for finite element analysis, there are different sources of nonlinearity. One is material nonlinearity, and this is the thing you saw here ultimately just at the beginning, right? The stress-strain relationship, which is linear in the red line or on the red line, but as soon as you hit yielding point, it's not linear anymore. And it becomes a problem for linear FEA if you have strains higher than this point, right? So material nonlinearity is one thing. The other thing is geometric nonlinearity and something like contacts. So let me just quickly show what I mean. We have, for example, our cantilever beam, right? And we have a loading here. And this cantilever beam, because of the loading, it deflects. Now, first thing is the geometry changes. You see as it deflects until here, the lever gets shorter, right? So it was this long, but it gets shorter because of the geometric deformation. And this makes the structure change the stiffness matrix because, yeah, you have a different system. You have a deformed system now. And basically with nonlinear FE or large displacement, you will update your stiffness matrix. So just imagine you had modeled this as one element. The stiffness matrix would stay the same without a large displacement on. With large displacement on, or with geometric nonlinearity enabled, it means that the stiffness matrix of this element will update according to the deformation. Well, alright, for one element it would not be that ideal in this case because you don't have a curvature, right? It will stay a straight line, but either way, the shortage in the lever would get updated. So that's geometric nonlinearity. You can see that, for example, as with a fishing rod, right? So it turns, you have large rotations. That's usually a sign when to include nonlinearity in geometric context. It's with large rotations. That's one thing. Where to consider that. Alright, so that was geometric nonlinearity, and contact is pretty much a same set of nonlinearity. You have your cantilever, it will deflect, and let's say you have a surface here. And as soon as you have contacts enabled, as soon as it will deflect onto this point, the stiffness will increase drastically because you have a different loading setting, and that makes it nonlinear as well. So this is just another source of nonlinearity. All right, so after we talked about this a little bit, now let's focus on the main topic, and this is the material nonlinearity. So maybe you saw that a bunch of times, the stress-strain relationship, singular. In linear FEA, you're valid on this line. If you go beyond the yielding point, which I will mark maybe like here, and here's your failure. So if this is a curve, you're valid until this point with linear FEA. After that, it gets wrong. So why does it get wrong, or what's the basic scenario here? Well, in FEA, you have your model consisting of elements you know, how they behave geometrically, and now you pose a external load, and you calculate the internal response until equilibrium, which means you get a displacement field, a strain field, and from the strain field you will calculate the stresses. So if you have a stress point here, in linear FE, you would go up to here and would say, all right, this is my stress value. But in reality, you would be here. And that's the thing where you have this large stress values in your FEA, which happens quite a lot in linear FEA. It does not happen with nonlinear FEA because you will see how this is modeled in a bit. But then you will have the higher strain values, right? So, all right. Yeah. Now, as we saw the differences, or when to include the nonlinear material model, next thing we want to see here is how to model it. Because, well, you don't have this curve modeled entirely. You could. There's quite popular approach to just piecewise linear go this curve and have different slopes and model it like this. This is one thing. And a subset of that, which is the most easy one and also most used one, is the bilinear approach, where you just have two slopes. A linear one, which I just call E, and a slope on the plastic region, which I call ET. Now, the problem here a bit is, you will also see that in a tutorial, is that it is defined a little bit awkwardly. Well, at first you see that as being maybe a little bit awkward. If we're scrolling down to the material setup here, you will see there's this H value, which seems to be a constant. And it is a relationship between E, T, and E. It's called a hardening slope, and I want to dig around that a little bit, because maybe this equation makes a lot of sense to you. At the beginning, for me, it did not, but we will see it in a bit. So we'll just use a whiteboard again. So if we are on a point right here, the delta in epsilon, so difference in epsilon, consists of a plastic part and also an elastic part. So if you just draw the parallel to the elastic region, you could see every point here, you would have a elastic part and a plastic part. It's hard to see, but from an equation standpoint, it makes a lot of sense. So your delta epsilon in total equals a delta epsilon which is elastic plus a delta epsilon which is plastic, which comes from the plastic strain, right? Maybe also, yeah, we could talk around this topic maybe for hours, but just because it seems so obvious here, a ideal plastic material would be like this, that as soon as you hit yielding point, it will just be a flat line, which means it does not increase in stress, but just the strain will get larger. But usually you have elastoplastic material, which is kind of this, what you see here. You have increasing stress over increasing strain, but not at the higher slope as with the linear model. That's why it's called bilinear model, because you have two linear regions. And as soon as you hit yielding point, you will have the different slope, and it will have larger strains on lesser delta stresses. So going back to the equations, you have for sure you know the equation for 1D sigma, the stress equals E times epsilon. And we will use this in the form of delta. So delta sigma equals E times delta epsilon. And now we just use this over here. So I could write delta sigma divided by E total equals delta sigma divided by E. So E is just a normal linear one, plus delta sigma divided by E plastic. And this E plastic is the H value. This is the hardening slope, the work hardening slope. So let's just make some basic maths here. It's the most embarrassing part if I do here some stupid mistakes. But we will divide by delta sigma, and we will multiply with with E, and we will multiply with E plastic. So we have E plastic divided by ET equals E plastic divided by E plus E plastic divided by E plastic. Now we can short those out, and we have remaining. I will bring this ET over here, so E plastic equals ET times no, I will not make this like here, but rather so, plus E times E, ET times E. So ET, this was from the multiplication over here. Now what I'm interested in is the H value, or the E plastic. So I will bring this over. So E plastic E minus ET equals, so I brought this over, equals E total E. That's just this one. And now E plastic equals E total times E divided by E minus E total. And that's the same if you bring that E down in the denominator. It's ET divided by 1 minus E divided by E. And this should be the equation we saw here. Let me check. Yeah. All right. So this is how we derive that. And this is the work hardening slope, so the plasticity modulus, you could also call that. And this is the parameter we will be using in the Hypermesh model. So I hope this made it a little bit more clearer. All right, the other things we will tackle as we work through the model. So what I will do now is I have already loaded this one. I've already loaded the model here, and I will just do the steps in the tutorial, talk a little bit about it, and yeah, just walk you through the model. So what do we have here? We have this plate. Let's go quickly back to this tutorial. So what it is, it's a plate which is loaded with a pressure, and we have it supported on both ends. We have a fixed end and a free end. Rotation should be free on both sides, I think. Seems like it. And all right, we have unit system, which seems to be the MPA system. We have the geometric properties, which we always can check quickly with F4 to just see if it's, yeah, 1000 millimeter here. So we have the same or the correct units. And what else do we have? We have material. So it's standard steel with the density to Poisson ratio, and yeah, yield stress is 100 MPAs. Rather low. And yeah, tangential modulus is 20,000. All right, yeah. Okay, so and here we have the pressure, so it's 0.02 megapascals applied normal to the plate. Also a thing to notice, yeah, follower loads, also a topic, maybe I can just briefly talk about this. It is, if you have your cantilever beam, and this deflects, normally the load will stay the same direction, so it will keep pointing downward. But if you have follower loads on, it will be kept normal to the element, so it will move according to the large displacement. That's also some sort to to remember if you're doing nonlinear analysis. All right. Okay. So let me just go through the tutorial. So we launched Hypermesh. We had the user profile set to Optistruct. All right. We have imported this, and now the first thing we want to do is set up the material. So go to this field here. MUD1, double click here, takes you to the materials browser. Now you have this MUD1 card, and there is no MUD S1 card enabled yet. So we will enable this and set the following values. So the type will be plastic. And we have 22,000 for the H value. See if the tooltip also says something interesting for us. Work hardening slope. Slope of stress versus plastic strain in units of stress. For perfectly plastic cases, H equals 0. That's what I was talking about. The slope will be 0 because it's a flat line. Right. Okay, so 22,000 is here, and then we have this limit 1 value to set to 100. This should be the yield strength. Initial yield point, yeah. Alright, so the next thing the tutorial wants me to do is update the property. So let's see if the property is already done here. Double check if we did forget anything on the material. No, that seems to be good. So this can be closed. Back to the model. Here are the property and P shell. P shell here. So we want to update it as the material mat1. So this is okay. This is already done. Alright, so it's a material with the thickness of the shell will be 4. You can also check this by enabling the thickness here. Let's see. 2D shells, yeah, you can see it suddenly became a thickness. This is always a good idea to check that if the property assignment worked correctly and if it has a shell thickness assigned to it. Right? Now the boundary conditions. Boundary conditions will be pretty standard, so nothing fancy or nothing new in this case compared to the other models we did on this channel. So what we will be doing here in the boundary conditions. So we will create a load collector. Well, we can choose and pick a color, and we will set some constraints on the left side and on the right side. On the left side, we will select DOF1 and DOF3, which is the X direction, translational, and the Z direction, translational, which is fixed. That makes sense. Yeah, this should be in this case the let's see about this. It's strange that you don't have to constrain the y direction. It seems that I think this is the numbers of the IDs, right? Well, we will see about this. So I will just do it according to the tutorial. Alright. Back to here. So we create a load collector. Create load collector. And this load collector will be named LC underscore SPC. SPC for single constraint, no card image. And now we can create the constraints. So analyzes constraints. Now, wants me to have it set like this. X is pointing to the right. Now we will select all nodes here. So like this. And we want to select DOF1 and DOF3 and deselect all others. Right, great. Now on the other side, we will just create a DOF3 boundary condition. So movement in Z direction will be constrained. And that's about it. Now, uniform pressure. Also show that to you in the tutorial. So we will create another load collector named LC implicit. And we will have it set to a p load of 0.02. Yes, that's okay. And then we will be coming to this nonlinear part. This will be a little bit more interesting for the folks who already did the linear analysis and maybe are bored at this point. So let's just quickly create this. So I create another load collector. And how should we call it? LC underscore implode. Alright, no card image as well here. And now analysis, we have pressures here. And select all elements. Yeah. And we can also pick the faces. That's also okay. Let's see if that works. And the magnitude is minus 0.02. And normal is alright. P-load 4 is good. Yeah. But it wants me to have it set on P-load. Well, that's also okay. Now create, and you will see the loading. Actually, I cannot see the arrows. Let's see if we can change that. Yeah. Well, alright, seems good. So it's pointing downwards. We have a P-load here assigned to it, and it's set to 0.02. Alright. Now, as this is set, we can now switch to the nonlinear parameters. Now, we also want to create a load collector for that. So create a load collector. It tells me to name it LC underscore NLParm, which is short for nonlinear parameters. And this will have a card image. So here we will choose the NLParm card image.
A few moments later.
All right. I think I found it, but it's rather unconventional. It seems that they have got rid of the nonlinear parameter load collector card. So I will just delete this. Now let's go back to the model. What we did here, we have two load collectors, and it's not called a load collector and not called a load collector anymore, but it's called a load step input now. Right? And now let's see if we have nonlinear parameters. So this should be it. All right, back to it. So we have to define this. Now let's just call it NLParm. And now the thing is, the values will stay the same. So what this will do is it will say that we want to have the convergence checked on 3 separate values. U is displacement, P is loading, and W is work. So what convergence means, or if convergence is achieved, that means in 2 consecutive iterations, the changes are small enough. So it is considered to be converged. That's all that means. And here you saying that you want to have the displacement converged, so it should not move. You have the loads converged, no loads changed, and you have the work converged, so no energy change. So it checks for all 3, and we also can define the values, but the tutorial suggests us to just go with the standard values, which are those 3. So epsilon, U, P, and W, those are the values which are used for the different convergence criteria, U, P, and W, respectively. Alright, so dt equals to 0, that's also the standard value. There's different ways of defining your time step. You could choose to specify a number of increments, or you have maybe also choose a number of time steps or time increments, which is the delta t, and you also can change or specify a number of maximum iterations, but we will go with the default values. All right, so we have created our load step inputs here. Let's see if we can create another one. Yes, which is the NL out. So what we want to see later on in the model, so NL out is nonlinear output. And we want to have that the number of the n int to set to 10. Let's see. So NL out parameters, output parameters, yes. Right. So this is the nonlinear incremental output. So every 10 iterations will have a output. At least that seems to me to be this case, right? We'll check if that's the case. All right, so this is it for the nonlinear outputs. Used to be load collectors, they are not anymore. Those are load step inputs now. And now we want to check also or create global output requests. Always a good idea. You do this with the control cards here, so analyzers and then control cards. And then it is called a global output request. So you can go to next global output requests. And we want to see the displacement and the L force. So this is the elemental force. O load. Just this one. Stress and strain. Alright, we will go to with the standard values here. It will all be written to the H3D file. And we're set with that. And another thing is also in the control cards, we go to the control cards param, which should be here. Param. And here you will set the hash assembly, which is just a way of saving memory with nonlinear models, which is advised. Actually, for this small model, I don't think it's necessary, but it's a good practice for larger models if you have those later on. And also the large displacements is also activated here, going down here to large displacement and set large displacement to 1. So this activates the geometric nonlinearity. All right, now we have done that. Next up is creating the load step. So I already clicked here and set this to nonlinear static. The tutorial said it should be nonlinear quasi-static, but this is not longer there anymore. I'm assuming that nonlinear static is the new name for this. And we will use this. So give it a name, nonlinear large displacement. Also, we couldn't do studies here, right? So one with large displacement, one without large displacements. I think control cards are set either way, so you should, or you would have to use different models. Now, name is set, SPC, that should be easy. Load, or nonlinear load. No, it's a static load. So load, implicit load. Now, yeah, we have the nonlinear parameters. This. And I think we did not name it correctly, but the nonlinear out. There is no nonlinear out. Ah, there it is. So nonlinear out will be this collector. I will rename that in a second. Yeah, and I will create this one first. And then I will create another load collector, which is a linear static, so we can compare the two different load steps later on. So use that to be linear static. We have the load collector, load, an SPC, nothing else set. Create this as well. And check always if those are all done here. Yeah, so we have two load steps here. That seems good. And now, before I submit a job, just because we like to tidy the things up here, load step inputs, there should be two in here. I will just call that NL out so that it is clear what this was. And I will just save this as a model. Let's here. No, a good idea to do it there. Well, classic one, do it on the desktop. So, OS tutorial. And I will just call it nonlinear bending plate.hm. And also, this save action does, it sets a default path for submitting a job onto this. So I just have to do nothing else but click run. And this will do it. Well, the tutorial said I should maybe also export all, stuff like that, but I think this is okay as well. Now we can see it's using 830 megabytes of RAM, and we'll use the mumps solver, and it may allocate memory in different modes, in or out. So in core would mean the whole stiffness matrix is set into the RAM, and that's the most efficient way, most fast way, but also the hardware intensive way of calculating things. Now, yeah, that's about it. Now we can check the results. Takes a bit. So go to the solver directory. Show that to you here. So this is the things which got outputted here. So we have different files. We have this HTML file which shows a report. If I can find it, should be here. Well, actually, it's not. But we have this played out file. This is a normal output, right? Find it. Ah, hidden. Alright, so we have the output here. And what I wanted to show you, or what also in the tutorial is shown here, is the iterations. So you can see the nonlinear values for the convergence, displacement, loading, and work. And you see that this is converged because it's less than the values we specified for a iteration or 2 consecutive iterations to be considered as converged. So this is also a good way to check if something went wrong. If you have not converged, or if your simulation did not converge, you can see what goes wrong. Is it a displacement? Is it a loading? And this can give you hints on where to check next. Now, for result comparison, like this is your model, right? And you have your nonlinear large displacement analysis. You can check the displacements, and here you have 29 millimeters of displacement. You can animate it. Maybe that's a bit too fast. Oops. Sorry. A little too fast. But I just want to show you the difference of the different load steps. So this is the nonlinear one with 29 millimeters. And it has, let's check the element stresses. You get roughly about 234. And yeah, now let's compare that to the linear model. For the linear model, you have this 936 megapascal and lots, far less displacement, I would guess. 24. It's not that much less, but it's less displacement, but higher stresses, and that's the case here because as I showed that to you here, in the linear model, you're up here, and with the nonlinear model, you're ending up on a lower value, but with larger deformations because you would have larger, less stress, larger strains. Yeah. All right. Let's look into the tutorial, how they sum up the things here. Now you can see the differences here, and that we indeed built the model correctly. The displacements, you have that 29 millimeters here, 24 millimeters there. Element stresses. All right. And then also what's interesting, the plastic strain, because if you have a nonlinear model and you calculate the nonlinear model, what you want to see then is not so much the stresses, because it will not exceed the yielding point too much, but rather more what's interesting to you is the plastic strain, and if it's still acceptable to have higher plastic strains in areas of your interest. So check more for plastic strain, and yeah, that's it. So that was a very easy introduction to nonlinear modeling with HyperWorks. So what we covered, to just summarize it shortly, we covered a little bit the stress-strain relationship, the different ways where nonlinearity will occur in your model, geometric, material, and stuffs like contact. And then we build up the model here, which was rather the same as with anything, but we have this nonlinear parameters, which is not a load collector card anymore, it's a load step input card. You have to know this. And we talked a little bit about the conversion values for displacement, loading, and work, and set some output values for the nonlinear simulation. And we did run the simulation and compared it to the linear simulation and ended up comparing the two outputs. So I hope you liked that. If you have any questions, comments, feel free to comment down below. And I would be happy if you return once again, and hope to see you